Hello everyone, your Dr. Zia Tahir here. This video tutorial is vibration analysis of cantilever beam with tip mass in ANSYS workbench. So analysis for natural frequency and mode shape is performed in ANSYS workbench. So a steel cantilever beam shown in figure that carries a mass at its end. So dimensions of cantilever beam are length, width, and depth is 0.4064 meter. Its width is 25.4 millimeter. Depth is 3.175 millimeter. And a steel cube here is attached, and the dimension of cube is 25.4 millimeter, and that is fixed at free end of the beam. Modulus of elasticity, Poisson's ratio, and density of steel is taken as 210 gigapascal, 0.37850 respectively. So required is to determine natural frequency and mode shape of first three modes of vibration and to compare ANSYS results with theoretical or analytical results. So the steps for model analysis of cantilever beam in ANSYS workbench. So these are the 7 steps. So project to start, then add materials, select analysis type, and then uh, create geometry in design modeler, and then assign material mesh, and then model analysis setting, applying boundary condition, defining deformation, and then getting results, and finally comparison with analytical results. So for the comparison and analytical results, I am going to use that book, Piezoelectric Energy Harvesting First Edition, and it's published in 2011, and that is Appendix C of that book, Model Analysis of a Uniform Cantilever Beam with a Tip Mass, and then a paper published in 2021, revisited the free vibration of cantilever beam with an asymmetric attached tip mass. So first step is to start a project model and then save model. So that is a ANSYS workbench, how it looks like. And here you have model. So double click on model. Okay, so that will go in the project schematic model, and then I'm going to save that. So I've saved that project. So once it's saved, so then we can use all these steps here. Next step is engineering data, need to add material, and for material is linear elastic, isotropic elasticity, and then physical properties, density, and then need to save material. So here in the engineering data, double click on engineering data, and then on engineering data here, click here to add new material. So that new material is steel, so it is created. Now need to add density in it, and then isotropic elasticity in it. So density is 7850 kilogram per meter cubed. Young's modulus is 210 e raised per 9, and Poisson's ratio is 0.3. So need to save this. So once saved, material steel is saved. Now close it. The next step in the geometry, start analysis type and basic geometry options. Solid bodies analysis type is 3D. So here, click on the geometry. So here you have that project schematic geometry and solid bodies, and then analysis type is 3D. Next step is in the design, need to start design modular geometry, and then these 3 steps need to apply. Okay, so I am going to do that step by step. So here you have geometry, right click on that. Now there are two options, space claim geometry and design modular geometry. I am going to use that new design modeler geometry and a new window of design modeler will open. So that is the design modeler. So in the design modeler, first need to sketch and then extrude, giving depth and then generate. First, I'm going to generate beam and then on that beam, I'm going to sketch mass. So I have design modeler here. So I'm going for XY plane and that is sketching. In the sketching, I'll go to setting, grid on, and then major grid size, I am going to use as zero point 0.1. Okay, so and then I want to draw it an XY plane. So that is XY plane. So grid is not being shown here. So I need to zoom in and then it will show there. Okay, so then here in the draw a triangle, just a random triangle. Okay, and then dimensions, general, so it's both dimensions. So height h1 is the depth of this beam, which is 20, width of beam 25.4 e raised power minus 3, and then vertical is that is 3.175 e raised power minus 3. So that is here is that tiny one. So like in modify, you can drag that one. Okay, so that is being dragged. Okay, so that is being dragged. So now that is a sketch and generate. So once is being generated, and then the next one is extrude and go to isometric view, and then its depth is the length of the beam, which is 0.4064. Okay, and so and then generate because once is being generated. So then that is the beam. Okay, so now sketch, so that is being generated. Now we need to create a new plane and type from face, then select base face and then generate. So for this one, you have option here is a new plane. Click on new plane and that is plane 4. Okay, so type is from face and then base face not selected. So here is a base selected, applied, and now generate. So now new plane is being generated, and on this new plane, now I am going to sketch that mass. So I can sketch here or I can sketch on the other side. Okay, so let's zoom that part. Okay, so now click plane 4. So after clicking, now need to go sketch. Okay, so you can add here in the setting, you can grid on and then like 0.1. Okay, so now draw a rectangle starting from there and then add dimensions to that. dimensions, general. Okay, so both dimensions are 25.4 e minus 3, and the other one is also 25.4 e minus 3. Okay, and then generate. So once it is being generated, so in the modeling, and here you can see that is a sketch generated. Okay, so now by clicking on that, and then now extrude. Okay, and then for that extrude, now it is giving extrusion upward. So I am going to extrude depth 25.4 into 10 to the base power minus 3. So that is extrude and then generate. So now you can see that here, so that the second one is being extruded. Okay, this one. So now with this, that in design modular geometry, so the beam is being now generated. Okay, so I'm going to save it and then close it. So the next step, need to go model, and then in geometry need to assign material. Okay, so here model, double click on model and it will open a ANSYS mechanical. Now this one, model mechanical or ANSYS mechanical, is being opened as a new window. Check the units. So they must be the standard one which you are using. And then click on geometry, solid, and then assign material. So material is the one which I have created. So now the material is steel, which is assigned in the geometry. The next step is to mesh, and then element size is 2.5 millimeter, and then generate that. Okay, so here is mesh. Okay, element size default. So I'm using is 22.5 millimeter, 2.5 e raised power minus 3. Okay, and then generate. So uh, auto generation of mesh. The mesh is not that much perfect as you can see from here. Okay, so it's not that perfect, but for this one you need to create partition, like you need to create partition or split edges, and then from that split edges you need to then create, like with the face meshing, and then by applying sizing. But anyway, the mesh is now ready. Next step in the setup, number 5, model analysis setting, and need to set modes. So here in the model, that is analysis setting and maximum modes to find. So you need to select 5 here. Okay, so if there is any damping, so you can add damping value, but there is no damping. Okay, because we are considering free vibration, so no damping. So analysis setting and 5 are the maximum modes to find. They are selected here. Next step is in the setup need to apply boundary conditions, and for that one need to go environment, sports, and fixed. So here sports and then fixed there. Okay, it says that scoping method geometry selection, so need to add on this side. So just rotate that one and select edge from here. So selected, applied. So one face is being selected, and then that is isometric. So this end is fixed, So a fixed board, you can see it's there. Next step in the solution, need to add deformation total, and that is to get more shapes. Okay, and for natural frequencies, that mod in the setup model you have already assigned number of modes. So for that in solution, deformation total. So here in the solution, click on the solution, and that is the total deformation, and I'm going to rename that as mod 1. Okay, and here it is mod 1. So from here, like for which shape deformation is required, like for which mod shape, so it can be changed here. So I'm going to duplicate that to get the next one mod shape, which is 2, and then need to change here for second. So in the similar way, I'm going to duplicate for 5. So now the total deformation for all modes 1, 2, 3, that is the third mode, then fourth mode, and then fifth mode. So they are added in the solution. Next step is solve, and it's very simple. So just uh, click on the solution and then solve. So it will take some time to solve. The next step is in the results need to get total information, and then it is show undeformed model on it. So now that is the first mode, that is the second mode, third, fourth, and that is the fifth mode. And on the edges, show undeformed model. Okay, like that. This is undeformed model, so that is the first mode. And the first mode is in YZ plane. And natural frequency for the first mode is 9.58. Okay, then that is the second mode, but this second mode is in XZ plane, so that is not in YZ plane, so that is irrelevant. Then the third mode is relevant because it is in YZ plane. Okay, and then its natural frequency is 79.95. And then the fourth mode is again that is not relevant because not in YZ plane. And then finally the fifth mode is relevant, so its natural frequency is 235, and that is in YZ plane. So here the relevant is first mode, then the third mode, and then fifth mode. So we can say this is the first mode, that is second mode, and that is the third mode. So the next step is comparison with analytical results. For the comparison with analytical results, I have here from this paper. So that is there is an equation in this revisited on free vibration of cantilever beam, and here is approximate analytical solution for the first order. I got that in MATLAB for the first order. So the natural frequency comes as 9.2246, and for the first mode here the natural frequency is 9.51, so it is slightly higher than that. And then for other modes, so here in the book, that is piezoelectric energy harvesting appendix C, model analysis of uniform cantilever beam with tip mass, and there is solution for that on, yeah, C18. on. So here C11. So by rearranging that, we can calculate omega, which is m L raised by 4. M is the mass per unit length, and then EI. So once that lambda is known. So C18 equation, when it's being solved for non-zero values of lambda. So first, second, third, fourth roots of this equation, they will give values of lambda corresponding to first, second, third mode. So by solving this equation, so values of lambda can be calculated. So once these values are calculated, so by substituting in C11, so natural frequencies for each mode is calculated, and once it is being lambda is calculated using C19 along with C20, then eigenfunction or mode shape can be plotted. So I have just calculated natural frequencies, and natural frequencies of cantilever beams is tip mass, and the first is 9.21, second one is 77.20. So the second one here is 79.995, and the third one here is 235.78, and I got that as 236.16. So first and second, they are pretty close, but the first and third, but the second one is slightly different. So because these are analytical results, so, so they might be slightly different from solution to solution, that which type of solution you are using. Like as in this one, so the same problem is solved using two methods. One is by separating variables, and the other one by Laplace transform. Like as so, traditional method of separation of variable and method of Laplace transform. So the same problem is being solved, and then the results from here. So they are slightly different. So now these analytical results from the book piezoelectric harvesting. So the results are they are relatively closer to they are relatively closer to ANSYS results. So now the problem is being solved, and the numerical results from ANSYS workbench, they are compared with analytical results. And that's a summary. The first need to start a project schematic model and save model, then add material. So requirement for model analysis is density and then modulus of elasticity. Okay, and then in the geometry need to start analysis type, basic geometry option, solid bodies, and then analysis type is 3D. Then need to start design modeler. First need to sketch beam, and then need to sketch mass on it. Then the geometry need to assign materials. Then mesh model, element size I kept it 2.5 and using the default value. Then need to model analysis setting, need to set that maximum modes required are 5, so they will just give natural frequency, and then need to apply boundary condition which are fixed, and then to get mode shape deformation total, and for each mode, like uh, total deformation is required, and then after total then solution, and the results total deformation and natural frequency is being displayed, and finally results are compared. So thank you very much for watching.